All right, so respond to the attendance poll, letter C, and happy Friday, you guys. Hope you guys are doing well, surviving your 4th week of school. We only have, what, 6 more weeks of lecture and finals after that, if you even have finals, so it's probably like all group projects for you guys at this point, maybe, I don't know. So, okay. Today, we are not going to talk Monte Carlo methods. We are going to talk Bayesian statistics because I think one of the most important applications of these Monte Carlo methods, especially Markov chain Monte Carlo, is in the context of Bayesian statistics, and therefore we need to spend a little bit of time talking Bayesian statistics before we can get into how to apply these MCMC methods for Bayesian statistics, okay? So today, we will do Bayesian statistics. There is a textbook that I have put in the syllabus, but I've linked on CCLE because when I didn't do that last quarter, people had trouble finding the textbook. All they had to do was click the link in the syllabus, but you know, they didn't. Anyway, so here it is. This is my favorite textbook on Bayesian statistics. And it's free as long as you are connected to the UCLA network, okay? Well, maybe it's accessible for UCLA students. I don't want to say free because you guys paid a lot of money to be here at this school, but one of the benefits of going to UCLA is that you get access to UCLA's library, in which this Doing Bayesian Data Analysis textbook is available. And of course, if you want to spend the money and have a hard copy book, you can spend the money. But I don't even put requisitions in the bookstore because, in my experience, 0 people buy the textbook. I don't know. But anyway, it's got puppies on the corner. It's great. So I recommend reading Chapter 2. This kind of gives you a big picture overview of what Bayesian statistics is all about. If you need to, you can review Chapter 5 on Bayes' rule, but I'm hoping you guys remember Bayes' rule from your probability classes and whatnot. And then and we'll spend a good amount of time in Chapter 6 and Chapter 7, okay? So anyway, read those chapters. And in my opinion, the textbook's written at a very accessible level. So, okay. So we'll talk. Okay. So the kind of the big idea with Bayesian statistics is that what we can think of this as, and this is what the author of the textbook says, is Bayesian inference is reallocation of credibility across probabilities. And I think this is actually a brilliant definition here, okay? Okay, and the idea is you might see some kind of output, or you might see something, and based on whatever you hear, you start off with a set of credible possibilities. Okay, so prior to seeing data, you begin with some credible possibilities. And then you assess the likelihood of your observed data under each of these possibilities, prior possibilities. Of your data or evidence based on each of these possibilities. So you have to assess all possibilities is what we do. And then at the end, we update the credibility, which we're kind of using as a substitute word for probability. The credibility of the possibilities, okay? And I think I've outlined this in Wednesday's lecture as well, but it's worth repeating because this is truly the heart of what Bayesian statistics or Bayesian inference is all about, okay? And it doesn't have to necessarily remain in the context of statistics and data and all of this, because our worldview oftentimes is like Bayesian inference, okay? So if you're a detective and you are solving a crime mystery and you start off with certain possibilities, you might have a list of suspects, okay? There might be 4 suspects that you have, or I don't know what you, maybe we should say 4 persons of interest, okay? And you look at the data, you look at the evidence that you have, and you say, how likely is it to have this evidence if this person of interest is the perpetrator of the crime, you know? How likely is it, you know, to have, I'm trying to think of an example here, but, you know, if you look at the, maybe there were footprints left in the dirt or something, and you look at the size of the person of interest's crime, and that person's feet are much bigger than the footprints left behind, then, so prior to looking at the data or evidence, you know, maybe all 4 of these people have equal credibility of being the criminal, okay? But then after assessing the evidence, you might say, well, this person's feet, this suspect's feet are huge compared to the footprints left at the crime scene, and therefore the probability, our beliefs about this person being the true suspect will drop in light of the evidence, okay? And there might be other things, and as you go through the evidence and the data that you have, you might find that 3 of the persons of interest, their credibility of being the suspect or their probabilities of being the suspect get lower and lower and lower. Your beliefs that they are the suspect get lower, and you might even eliminate the possibility that they are the suspect, and you are left with 1 person, okay? And there's, what is it? Once you eliminate the possibilities that are impossible, I don't know how it goes, but once you eliminate the impossible scenarios, whatever's left, no matter how improbable, you know, must be the case, right? This goes something like that, and that's basically what we're doing, is we are eliminating things that are impossible or incredibly unlikely, and whatever is remaining must be the case, even if at the very beginning, prior to seeing any data, we might have said this is an improbable scenario. If all of the data eliminate the other possibilities, then what we have remaining is what we have, okay? Kind of the classic example that we use for Bayesian statistics, the introduction to this topic, is the beta binomial model, okay? And And I covered this a little bit in my 102B class, but we will take a look at it again. And this is covered thoroughly in Chapter 6 of the textbook, so make sure you do your reading. So we'll look at the beta binomial model, okay? So this is Chapter 6, okay? And today's lecture will be, we'll approach this subject from a strictly analytic perspective, okay? Which we will not do, which is not Monte Carlo, okay? Which is not Monte Carlo methods. We are doing it kind of the traditional analytic approach to this thing, okay? All right, let's talk about the binomial model, and let's talk about the beta distribution, okay? What is the binomial? When do we use the binomial distribution? Binomial distribution, the output or the x is the number of successes after n Bernoulli trials, right? Okay. And a Bernoulli trial can be thought of as just as a coin flip, in that there are two possible outcomes, yes or no. Success or failure. And the probability of success is P. Does that fit? Okay, barely. Okay. Are there any questions on this? Is this okay? All right, so the binomial is we're repeating a coin flip, or we're repeating some kind of Bernoulli trial n times, and we want to see how many successes we get. So something like we are going to flip the coin 5 times, and we ask how many times does it land heads, okay? Or, you know, we shoot a basketball 7 times, and we have to assume that each shot we take is independent of all other shots, which may or may not be the case, but we're going to make that assumption, and we say how many times does the basketball go into the basket, okay? And everything we do is either it is or it isn't, right? We pick a person at random from a group of people, and we ask what is, well, maybe we pick 7 people at random from a group, and we say what is the probability that 2 of these people have brown hair or something like that, okay? And the scenarios are either they do or they do not have brown hair, okay, for each of these things. So, so the output is the number of successes after n Bernoulli trials, and the probability of success is P, and we say for the binomial distribution, the probability of x is defined as n choose x, p to the x times 1 minus p raised to the n minus x. This is the probability of observing x success after n trials, and each trial has probability P of success. Okay, so that is the binomial distribution. Okay, what is the beta distribution? Let's talk about that. The beta distribution, we often throw this term out there, which probably doesn't make sense in the beginning, but we often call it the conjugate prior to the binomial. All right, but this is like such a, unless you've been dealing with Bayesian statistics, you see something like this and you're like, I know some of those words, but I mean, individually I think I know what these words are, but who knows, right? The beta can be thought of as a distribution of probabilities. Okay, we can think of this as a distribution of probabilities. Okay, so what if I tell you that we have some probability p, you know that p has to be a number between what and what? P has to be between 0 and 1, because that's how we define probabilities. So the beta distribution is defined only on the interval 0 to 1, okay? Distribution of probabilities, okay? It is defined on the interval 0 to 1 only. And and basically the height of the beta, the density of the beta, tells you what values of p are likely or unlikely, okay? The beta distribution tells you what values of p, kind of a probability, is likely or unlikely. Okay, and so here's a kind of an idea, is we've got this, I don't know, bucket, and someone says, I'm going to pour in, I don't know, M&Ms. We'll keep it simple. We'll say holiday M&Ms. So they're only red or green, okay? Except the person being obsessive, they're going to do them one at a time, and we're playing. This is like the most contrived scenario, but they let you see. All right, they say, all right, look, I'm going to put a red M&M in here. So you see one red M&M go in, and then you see another green, and then he says, look, I'm going to put a green M&M in there, okay? So you see one red and one green go in, and then he says, close your eyes, you can't look at what I'm going to do. And then you just hear him put a whole bunch more M&Ms in there, all right? And you don't know if you put like all red M&Ms, or if you put all green, or you put like an even mix, or like a bunch of red and some green, or whatever. You don't know, okay? So he does that, and then he says, open your eyes, okay? And the bucket is not transparent, and he says, all right, what proportion of M&Ms do you think are green, right? So at this point, you just know the answer, like you have no idea. So prior to looking at any data, you would say the proportion of red or green could be anything between like 0 and 1, right? I mean, not 0, not all the way 0 and not all the way 1, but pretty much any value in there is possible, right? So after seeing, all you know is that there's at least one red in there and there's at least one green in there. And you say, what is the probability, what's possible for the proportions? Basically, almost any value between 0 and 1 is possible here, okay? Is that all right? And that is represented by the beta 1-1 distribution, okay? So we put in a red. So you get to see this, all right? One red, green dot, and one, okay. So you see one red and one green go in, okay? And then you close your eyes. All right. They put in more M&Ms. Okay, so. And then you open your eyes. I don't know why it's important to open and close your eyes here, but it just makes it more fun, the mystery of it all. And we say, you know, what proportion, or like if I draw another M&M out of here, what is the probability the next M&M I draw is green, okay? Or we'll just say what proportion of M&Ms are green. Okay, and the answer is any value between 0 and 1, really, okay? You have no idea. And so the beta 1-1 distribution looks like this. On the interval 0 to 1, all of those values are equally likely, okay? So this means all values between 0 and 1 Yes.
Right on the beta 1-1.
Oh, well, this is how we define the beta distribution. So the beta distribution has these two shape parameters, okay? It's kind of like when you say the normal PDF is defined by mu and sigma, and it's like 1/2 root 2 pi sigma times e to the negative, you know, x minus mu quantity squared over sigma 2 sigma squared, something like that, right? It's just these are letters that go into the equation to determine the shape, okay? So this is known as the beta 1-1 distribution. You can kind of think of it as, you know, what's the probability if you just see one red and one green going in there? Kind of, yeah, it's not. All right, okay, so now we say, all right, so you say, well, I have no idea what probability or what proportion is green. It could really be anything between 0 and 1. And we say, all right, let's take a look at some data, all right? I'm going to draw out, to ensure that this is binomial, we'll take a M&M out, put it back in, shake it up, take another M&M out, and put it back in. So we're going to draw some M&Ms out with replacement, right? So we gather data. By drawing M&Ms with replacement. All right, so we draw one out. Okay, and then we'll put it back in and shake, all right? And then so we record, I don't know, 10 observations. Okay, after 10 observations, we'll say 3 green and 7 red. And so now we ask, well, what proportion of the bucket is green, right? So after looking at this data, And so, what do you think? Well, if we take a maximum likelihood approach and we just say, well, based on the data, what is the proportion that's most likely to be, what would we say? Thir 30% green, right? If the bucket is 30% green, then the data we observed is more likely than any other possibility, okay? But we also know that these draws were random, okay? And so it is possible that the bucket is mostly green and we just happen to, by random chance, only select a few red, okay? You know, technically it's possible that it's all green except for that one red, okay? And we just happen to get really, really weirdly lucky in drawing the red one 7 times. Although, you know, that would be incredibly unlikely, right? We would not believe that it is, you know, 99% green and 1% red. It's technically not impossible, but that would be so incredibly unlikely we wouldn't believe it, right? And on the other hand, we would also, you know, having 99% red and 1% green also seems really unlikely, okay, because we ended up drawing 3 green. But having something around 30% green and 70% red, that sounds pretty reasonable. 25% green and 75% red sounds not too unreasonable. Even something like 40% green and 60% red sounds okay, right? This is just based off of intuition here, right? But then as we get farther and farther, you know, if we said, do you think it was 60% green and 40% red? You'd say, it's not impossible, but that doesn't seem very likely, okay? And if we say, you know, do you think it was 5% green and 95% red? You'd also say, probably not, okay? It seems unlikely. And we would update our, so kind of based on intuition, what would we say? You know, 30% green seems very likely. Okay, you know, 25% to 35% green is also likely. Okay, but you know, 5% green is unlikely. I don't know, 60% green is unlikely, something like this, right? Okay, 99% green seems almost impossible. All right, is this okay for the intuitive sense? And so if we were to say, I want you to give me your intuition for every single possibility that green could be, right? So we're going to consider all possibilities between 0 and 1, because the proportion green could be, that's all the possibilities between 0 and 1. And I say, make a graph of what you think green would be. Probably our resulting distribution going from 0 to 1 would look something, if here's 0.5 and 1, 2, 3, 4, something around here, we would probably do something that looks like this, okay? I don't know, this is such a terrible drawing, but we'd probably, you know, I don't know. Does this seem like an okay picture? Maybe you'd make it more narrow or wider or whatever, however you feel. But this would probably be what our resulting picture might look like, okay? That's after drawing 10, right? What if we drew 1,000 M&Ms, okay? I draw 1,000 M&Ms and I end up getting 350 green and 650 red. Okay, so this is kind of our distribution of probabilities after 10. All right, and let's say, what if, or let's say I draw 1,000. Okay, so I draw 1,000 M&Ms with replacement from the bucket. And this is my data. My data says I got 350 green, 650 red. Okay, and now I ask, what is the probability of green? We'll say, what is the probability distribution of, the proportion green? Okay, so 99% green still seems very unlikely, but a bunch of other values also seem very unlikely. Now, having 50% green feels unlikely. Even something like 45% green doesn't feel like it's going to be very likely, right? And so the band of possibilities for what proportion of green is likely is going to be a lot more narrow because I've seen a lot more data, right? I've seen 1,000 data points, and so now we can have a discussion about which values of green are possible, but we can eliminate a lot of them, right? And we might say, okay, I really think the proportion that's green could really only be between like 30 and 40%, okay? I don't know, do you think values outside of that are also possible? Yeah. 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 Yeah, that was beta 1.1. Yeah, I want to discuss that at a later point, okay? I don't want us to get caught up in these parameters yet, okay? So, okay, but let's get back to here and we just say, all right, what window of values of the proportion P, what do you think are possible now that you've seen 1,000 data points and 350 of them were green? What do you think? There's no wrong answer, but we're basically, I'm trying to say, when you only saw 10, you'd say 60% is probably not likely, but it's possible, okay? But at this point, 60% is like practically impossible, right? And so now what's only kind of our window of possibilities is probably this very narrow band between, 30 to 40%, maybe even smaller, okay? So, only values between 30 and 40% seem even possible, okay? And values outside of that would have probabilities on the order of 0, okay? It's technically not impossible, so we don't want to say it's 0, because 0 is reserved only for things that are truly, truly, truly impossible. But for our practical lifetimes and purposes, they're on the order of 0 is what we want to say, okay? And so our distribution, our resulting distribution for 0 and 1, and this is 0.5 and 10, 20, 30, 40, and would probably look something like this, okay? This is our kind of our resulting distribution, okay? And this can still be defined, this is still a beta distribution. okay? And it's 9:40 already, man. Okay. It's hard. All right. Well, let's talk about the form of the beta distribution. So we're gonna go to Wikipedia, and we'll take a look. And I want to point out. So you go to Wikipedia and you type in the beta distribution, and it has all of these things. These are like kind of all the possible things. But let's look at the equation of the beta distribution, okay? The PDF of x raised to the a minus 1 times 1 minus x to the beta minus 1 divided by the beta function of alpha comma beta, where beta, alpha comma beta is gamma alpha times gamma beta divided by gamma alpha plus beta. And then you go, well, what is the gamma function? And then it's like this even crazier thing. And you look at this and it feels very scary. Well, I don't know, maybe when I first saw it, I was intimidated. But, okay, so the beta PDF. So the beta distribution is defined with parameters alpha and beta. There's two shape parameters, and it's on x to the alpha minus 1 times 1 minus x to the beta minus 1 divided by beta function alpha beta. Okay, and then we say beta alpha comma, here, I gotta write this over here. Gamma alpha times gamma beta divided by gamma alpha plus beta, okay? And then you go, well, what is the gamma function? Gamma of, let's look up the gamma function. Because the gamma function is pretty much the factorial function, but how do we define it? Yeah, it's 0 to infinity of x z minus 1 e to the negative x dx. Okay, that's how we define the gamma function. Okay. 0 to infinity. Oh, shoot. This is too hard. Okay. Okay. X to the z minus 1 e to the x dx. Okay. This is, you guys know the factorial, right? Factorial function. So you just, like, 3 factorial is 3 times 2 times 1, and you get 6. And, like, 4 factorial is 24. Okay. It's basically factorial but made continuous, okay? But it's factorial for x minus 1. So, gamma 3 would be the equivalent of 2 factorial. Okay, so anyway. So that's all it is, okay? So it's basically a continuous factorial function. But to get that mathematically to work out, because like if I said, what is 3.5 factorial, you wouldn't know what to do, right? But it's like we're drawing a smooth line that connects between 2 factorial and 3 factorial and 4 factorial, and you know we get something like z minus 1. Okay, but don't worry about this, all right? So all of this stuff just don't worry about it, okay? Because all that matters is the numerator. The numerator is the only important part, okay?
Question.
Yes?
So e to the negative.
E to the negative x. Yeah, I'm sure you are correct. Okay. The numerator is the only important part, all right? Numerator is important. Okay, that being x times alpha minus 1 times 1 minus x times beta minus 1, okay? And this stuff on the bottom, all it is you just think of this as a constant. It's just some constant c, so that the integral from 0 to 1, which is the entire span. We can technically go from negative infinity to positive infinity, but from 0 to 1 of the constant times the numerator dx is equal to 1, okay? That's all this is. All this stuff, this boils down to just a constant. So it integrates to 1, which is required to be a PDF, okay? For something to be a PDF, there's 2 requirements only. It has to be positive at 0 or greater everywhere, and it has to integrate to 1. So it's really just the numerator is the only important part, and this beta stuff on the bottom, which sounds crazy and complicated, is just there so that it integrates to 1, okay? And so if I just presented you x to the alpha minus 1 times 1 minus x to the beta minus 1, that feels a lot less scary, right? Oh, man, okay. Okay, well, let's just skip ahead just a tiny bit, okay? And we will get to the inference in a moment, and we'll I guess I'll have to talk about this on Monday. But we said beta 1 comma 1 looked like this from 0 to 1, okay? And then we said after 10 draws, our distribution from 0 to 1 would probably look like this, okay? So this is after 10 draws with 3 green and 7 red. And this would technically be a beta 4-8, okay? And then after 1,000 draws with 350 green and 650 red, we would have a beta 351, 651 distribution, which would look like this, okay? These are terrible pictures. I'm going to show you on R, and we'll get better pictures here, okay? But all this is kind of representing what we believe the probability don't worry about that midterm document there. All right, so let's say okay, so I'm going to do S is going to be a sequence from 0 to 1. Phi is equal to 0.001. Maybe for good fun, we'll do S is that. Okay. All right, so we'll call B11 will be d beta, the density, right, of S with shape parameters 1 and 1, okay? And then we'll have B, what did I say? B47, no, B48 is going to be d beta S48, and then B351, 651, that's too many letters. We'll just call it B351 is going to be d beta S351, 651. Okay. We will execute all of this. Let me do, let me find what the max of B351 is. 26, oh boy. All right, so we're gonna plot S against B11, type equals L, and then my Y limits will have to go from 0 to 27, 26 and a half, just so the plot fits, okay? And okay, so you can see this is at 1, right? So the uniform normal has a height of 1, So all values between 0 and 1 are equally likely with a height of 1. All right, and then we're going to add lines SB48, color equals, we'll do this one in red, okay? Color is not a red? Call. You are correct, okay. All right, so this is our, what it looks like here, and then we will throw in B351 in blue, and it looks like that. All right, demonstrating kind of our, what, after looking at our data, what we believe are possible values of, what was I saying? Of the probability of what proportion in the bucket are green, okay? So all of these things are technically beta distributions, and they're all representing what we believe is possible for what's in the bucket. Let me just kind of zoom in. Let me just change the Y limits. So, sorry, B351, we're gonna just redo this so this looks a little bit better, okay? So that, this is a little bit better. So we have, 0 to 1, equally likely before we look at any data, right? All you know is just one red and one green has gone in, we've dumped a whole bunch of stuff. Then we look at the data and we update what could be possible, right? So after seeing only 10, because we know there's a lot of probability and random chance involved with those 10 that we drew, we say, well, yeah, you know what? It's not likely, but it's possible that 60% of the M&Ms are green, and we just happen to get only 3 green and 7 red. That's possible, okay? And if I said, is it possible that only 10% of the M&Ms were green? And you go, yeah, that's possible, okay? But then after seeing 1,000 of them, really only values between 0.3 and 0.4 are even like remotely likely, where values very close to 35%. And then we can have anything in between also. So if I want to add lines S against D beta, we'll say 36 against 66, okay, with color equals green or something, we'd get something in between there, okay? Maybe, okay. And so that's, that's with 35% or something and things like that, okay? So, what becomes possible and improbable, we'll update. And so I'm debating how much time I want to spend on this. I guess on Monday we can go through some of the likelihood calculations. Please be sure to read chapters 2 and chapter 6 from the textbook. I think that will make your Monday lecture a lot better. Okay, all right. With that, have a great weekend. Some of you guys I'll see at Data Fest, so we'll see you there, and see you guys on Monday.